appreciate you all being here this afternoon for our first webinar in our series of webinars on the month that we've dedicated to lubrication, or as we like to call it, Lubiware. Just a few things I'd like to mention before we get started. We are doing this live, so if we have any technical difficulties, try to get that worked out as quickly as possible, so just bear with us. Normally things run rather smoothly. We are recording this, so you'll have a chance to go back and view it later or even share with a friend or a coworker. It will be archived on our website along with all of our previous webinars. All those webinars can be found underneath the training section of our website and then under on-demand education. And you'll just have to log into our website, and you'll then see a list of all the webinars that we've done, and they're broken down by application. You will be able to ask questions as we go through the webinar. If you have, we have a chance to do that at the end. Ray will certainly be able to answer a few of those, and then any that we don't get to, Ray will get those questions, and he'll be glad to answer those offline. Again, I'm Adrian Messer with UE Systems, and thank you again for being here today. We have with us Ray Garvey, who I'm going to make welcome here. I've known Ray for several years. Worked with him on various occasions at different conferences and training events, primarily with the University of Tennessee's Reliable Maintainability Center. Ray is a research and development engineer with Electrode Scientific, and he's also a certified lubrication specialist through the STLE. Prior to Electrode Scientific, he spent 25 years with CSI in Emerson, and then 11 years with Oak Ridge National Labs in Oak Ridge, Tennessee, and he's also retired from the U.S. Army. So without further ado, I'm just going to transition over and make Ray the presenter, and we'll get started. Okay, Ray, should be all yours now. Should be able to do show my screen there, and there we go. There it is.
Okay. Good afternoon. Good morning to those in the West. It's good to be here. My name's Ray Garvey. As Adrian. Oil analysis and lubrication and ultrasonics are very much connected, because a lot of what makes ultrasound meaningful is actually the tribology of stresses and relative motion. So I'll try and make that connection a couple times during this presentation, and we'll proceed from here. I will say that from oil analysis point of view, which is another condition monitoring technology besides just ultrasound or vibration or motor analysis, this the oil analysis involves looking at three things. That's the wear condition of a machine, the contamination condition of the lubricant system, and chemistry condition of the lubricant. Those three are pretty much independent, and we're gonna take a look at those and explain how the reliability of the system is measured using oil analysis. A brief orientation to this presentation is we'll introduce Spectro to those who are listening. That's who's paying my bills. So then we'll talk about how to identify root causes, root problems and their causes for why machines fail. This is totally independent of which technology you use to look at the root problems, but it does give you an insight on how lubrication helps see those in addition to the other technologies people use. Next is an oil analysis results that guide maintenance practices. Then I'll give a case history and mention a few references if somebody would like to go back and check up on some of the things that are presented in this presentation. We'll naturally have questions after that. Okay, just to begin with, I'll just say that lubrication is typically a program within an industrial plant or in a fleet of vehicles, fleet of equipment. The machinery that's running is running on a lubricant film. And to keep that healthy and keep the machine running for a long time without a lot of noise and power consumption, there's normally a program that says we have the right lubricant, it's been specified, purchased, it's stored properly, we check the level, we top off things, flush, clean, and dispose of the lubricants, do proper greasing, re-greasing. I know that's a big topic for that's very much the life of a system, because abrasion we'll talk about here in a little while. Training is a key aspect of a lubrication program, and we're doing a little bit of that today. And then oil analysis is another aspect of a lubrication program. The right place, right level, and right condition. Types of machines that you might see out there in the field. This one is one that's commonly found in fleet operations, like at a place where vehicles are brought in for maintenance. You can do an on-site oil analysis before you even change the oil or before you do any maintenance actions. And then an on-site for factories is a system that looks kind of like this. So we're going to introduce these kind of things that Spectro deals with. Okay, that's the introduction. Next, let's look at how to identify root problems and their causes. Uh, 85%, I would say, of the things that cause damage to a component and cause the component to be unfit for continued service really root back to one of these four: abrasion, corrosion, adhesion, or fatigue. And we're going to talk in detail about those. Another 15% of the problems, which are less common, deal with deposition, erosion, electrical discharge, and cavitation. So on this slide, I'll just talk about those last four, and I won't bring these up again. Deposition is what happens when you have a varnishing or a plating or accumulation of material on a surface. You know, a fan gets out of balance when it accumulates a bunch of debris on it. Valves and things start not functioning well when varnish accumulates on them. So that's a deposition problem. All the rest of these seven, the other 7 of 8 here, are all removal problems where they remove metal surfaces. Erosion is what happens when you have a blasting, like a sandblasting. Particles impinge on a surface. Electrical discharge is where you have electrical sparks that blast into a surface, typically where a bearing is carrying a current, and that's not supposed to happen. But when it does happen, because there's a gap there, the spark goes through the gap and blasts away a little bit of the material on the inner race or the outer race. Cavitation is what happens when you have a pressure collapse, weight that collapses like on the backside of an impeller. So those are 4 that we won't talk about today, but the other 4 we will talk about. And what we're going to learn is that some of the key measurements that people want to do, there are a lot of typical measurements, but the special ones that we need to really pay attention to have to do with looking for ferrous density measurement. That's a generic way to say I want to see particles that are iron and they are larger than 5 microns, because those are the real evidence of material damage from abrasion, corrosion, adhesion, or fatigue. They're going to typically show up big time in the ferrous density measurement. Particle counting, where we look for any kind of solid particles in the oil and count them, size them, classify them. That's a good way to look at contamination control and also check on the wear particles. And finally, particle shape classification. You'll see how important through this little section how important it is to be able to view the particle shape and determine the root cause. because the corrective action for abrasion is quite different from corrosion, adhesion, or fatigue. Each one of these is a different corrective action, so we need to know which one we're dealing with in order to correct the root problems. Okay, if I were to take a machine, pull a sample, look at the debris in the sample, typically you're going to have to filter the debris or have a very high-speed camera looking at the debris as it floats by the window of some kind of a sampling device. At any rate, you'll see particles, and the particles that we're concerned about here, because of the four main problems are abrasion, fatigue, adhesion, and corrosion, they're going to have different appearances. Now, abrasion is caused when a piece of dirt or sand gets trapped in a nip, like in between a roller and a race, a roller and an outer race or an inner race, or between the gear teeth that are coming together. Just about any place that a particle gets caught between two moving surfaces, if it's a hard particle, that hard particle will embed in the softer of the two surfaces, and it'll cut the harder of the two surfaces, and it'll cut it with a particle that looks like it came off of a lathe. And like the picture you see there on the lower right, it's pretty amazing. And abrasion is in many places public enemy number one. If you can eliminate the dust contamination, because sand or silica cuts through steel like a knife cuts through butter, so that process of cutting or abrading the surface is very damaging and shortens the life of machinery a great deal. Fatigue is what happens when rollers, it's kind of like the rolling contact disease, and rolling takes place in two kinds of machinery, or two kinds of components. One is obviously the rollers and the races and roller bearings, but also at the pitch lines of gears. There's a rolling contact right at the pitch line where the heavy loads are transferred. So that rolling contact produces in a very intense, what's called Hertzian shear strain right beneath the contact line, and that tends to cause fatigue, spall, and particles come out that look like chunks or platelets. Adhesion is what happens when we have inadequate lubrication. The sliding action. So this is the sliding contact disease. Fatigue is the rolling contact disease. Adhesion is when the lubricant film is broken through, and I'll talk about that here in a minute, then you're going to cause a lot of heat, a lot of friction, and a lot of material will be removed because the friction means you're doing a lot of work, and that work's going to be taking material off the surfaces. So inadequate lubrication is definitely a problem because the lubricant film's been broken through. Normally a roller separates itself from a race by a micron, or a kernel separates from a shaft by 75 or 100 microns or more. So that spacing is critical to keep the life of the load-bearing surfaces long. Corrosion is what happens when we have a corrosive media such as water or a process contaminant that attacks the metal surfaces chemically by oxidizing the metal surfaces, so that when a rubbing action takes place, it rubs off the soft oxide that formed. Okay, so let's take another look at these four things with a few examples. This is clearly a picture of abrasion. It looks like something you picked up off a machine shop floor. This kind of particle is an indication that you have some three-body abrasion, it's called. A lathe would be two-body abrasion, where you put a cutting tool into a mandrel. In this case, a piece of sand introduces itself into a tight space and starts cutting a groove in the opposing surface that it's contacting, and particles like this come off. Some more examples of abrasion. I mean, you really don't need to take, anybody can understand this once you look at it. So it is important to see what's inside of the lubricant. The lubricant does a nice job of carrying important evidence to you, the reliability team. And I've heard it said that if we didn't have blood in us, a doctor would squirt some in us just so they could pull it back out because it carries so much information that the doctor wants to know. We don't do that for machines, but it's fortunate that machines actually have their own fluid, which can be pulled out and sampled to carry this kind of very useful information to an interested observer. Okay, the abrasion is typically caused by dust or sand or silica. 2/5 of the world is covered by dirt, and dirt is one of the most serious problems in machinery health today. When it gets into the oil, I saw a study by a guy named Raymond Beyer where he tried to explain how do you remove metal fast, and he came up with these same mechanisms of abrasion and adhesion and fatigue and corrosion, and he gave the rates of material removal. If you really want to remove material fast, you use abrasion. You use like a grinding wheel or a cutting tool, and it removes metal fast. But if you want to remove it even faster, throw some lubricant down, cool things down, reduce the friction. You can cut twice as hard, or twice as fast, twice as deep with half as much load by just lubricating the dirt or sand or the cutting tool, whatever it is you're using. Unfortunately, the solution here is not to remove the lubricant, it's to remove the dirt. The dirt has to go, and we have what we call a contamination control program that sets target cleanliness levels for acceptable levels of particle counts, assuming that a lot of that debris is actually hard particles like dirt. Corrosion is basically, and here's some red oxides. I only use this example not because it's the most important picture, but everybody recognizes rust as being red. At least certain types of corrosion on metal, on steel are red. There's black oxides, which are far more common than red oxides, especially in a lubrication system. So a lot of the lubrication corrosion shows up as very fine black oxides that are rubbed off of a surface. And if you think about what happens when you grab an aluminum bar that has recently been machined, the bar looks shiny until you rub your hand down the length of it, and then your hand turns black. Now, why is your hand black? Does that mean your hand is highly abrasive? No, your hand's not abrasive. It's very soft compared to the metal aluminum. What's happening is that the aluminum oxide is so incredibly soft that it rubs right off. And that's what oxides are. They're not metal. They tend to rub off very easily. So rubbing plus corrosion removes metal. It's not a very fast process, but it is a very persistent process. And we need to try to keep the corrosive fluids like water and sulfur and fuels and stuff like that. We need to keep the corrosive media mitigated. Abrasion, which is also called adhesion, also called sliding wear or severe sliding wear or boundary wear. Now, all these names come up. I actually helped write a standard for terminology used in identifying these mechanisms and these particles. But adhesion it's actually not a pure term here. Adhesion applies to when you cold weld polish two metal surfaces like two steel bars or two steel plates, push them together, and they actually will cold weld together. That's the process of adhesion. And it's not exactly true here because many times the metals are dissimilar and they don't exactly go through an adhesion process. But we use the term incorrectly by talking about sliding contact as being adhesive or boundary lubrication is exactly correct. Boundary lubrication as opposed to dry contact. Normally friction between dry contact surfaces is quite high. Boundary lubrication simply means the metal to metal is contacting, load is transferring from one metal surface to another, but the lubricant is still in the low spots. There's still lubricant present, but the film has been broken through, and there's several reasons why the lubricant film has been broken through. There's some lubricant present, so the friction's not incredibly high, but it's still much higher than it should be. And why? It's because the most common problem is either low oil or no oil. Okay? I hate to tell you, but the first problem is not high tech. It's pretty simple. It has to do with oil level or oil presence at all. Now, The next three problems are like three legs of a stool. One is viscosity, two is load, and three is speed. When the machine is running slowly, it's like a person driving a boat towing a skier. You slow the boat down to a stop, and the skier will settle into the water up to his waist, where there's a nice float to hold him up. Okay, that slow speed means the two metal surfaces are going to drag across one another, because speed keeps the two surfaces apart, whether it's rollers or journals or whatever. You count a lot on the speed of the two surfaces, bringing the lubricant to separate the two surfaces. Okay, so speed's a big one. Load is a big one. The lubricant has a viscosity that tends to support a load, and a load that tends to be supported by a viscosity. So those two tend to be related to one another. And I won't go into the hydrodynamic and elastohydrodynamic, but there's a lot to this viscosity and load issues. And when you have too low viscosity, the machine gets into dry contact, or into, a boundary where you break through the lubricant film and you hit the boundary. That means you're going to have some kind of a metal-to-metal contact. And it generates a tremendous amount of ultrasonic noise, by the way. This is very common with sliding metal-to-metal contact. Is very common in lots and lots of machines. And it's normal in some machines. But it's abnormal in other ones. And if it's normal, then they find a way to deal with it. If the loads are low, then they just ignore it. If the loads are high and there's metal-to-metal contact, they deal with it by putting a boundary or an extreme pressure or an anti-wear additive in the oil to allow it to transfer compressive loads but not shear loads. So it's a weak link in the chain of shear strain or shear stress. And so they do something to break the shear transfer of force between a roller and a race, or between a sliding member and a stationary member. Okay, so additives do a lot. And then again, the effects of sliding contact, metal to metal, where you're actually transferring load metal to metal instead of metal to fluid to metal, that load transfer is going to, if it's abnormal, it's going to melt and smear and tear things apart pretty badly. You get a lot of black oxides. You remember I mentioned black oxides with rubbing wear, which is kind of like corrosion particles being removed. Well, it's also true here. You'll see black oxides a lot here. But in this case, you're going to see a bunch of other particles, which I'll show you pictures of. So I'm taking time on this slide because if you're calling into UE systems, you're probably interested in friction, and that's what this is all about. Friction shows up a lot when you have sliding contact. And I'll spend one more minute here to talk about the different parts of a roller bearing. There's an outer race, inner race, rollers, and a cage or a retainer. Those parts are all moving. Maybe the inner race is stationary or the outer race is stationary, but everything else is moving relative to that stationary part. They're all traveling at different rates and things like that, and they have different kind of contact. The rollers are in rolling contact against the two races, but they're in sliding contact with the retainer. And you can picture that in your mind as the retainer or the cage is actually just kind of keeping the balls or the rollers, whether there's balls or cylinders or whatever they are. The rollers are being kept apart, separated approximately an equal distance apart, and the thing that keeps them in their position relative to each other is a cage that slides against the rolling ball. It doesn't roll against them like the outer and inner races do. And that sliding contact is it requires about 75 microns or 3/1000 inch of lubricant to keep it lubricated, as opposed to the roller to race, which only takes a micron, because the very, very, very precise dimensions between the roller and the race, it tolerates incredible loads and very thin films to keep things apart. I tell you that thickness difference in the two films, the film of oil between the roller and the race, and the much, much thicker film between the roller and the cage, because the first one to get starved is going to be your cage to roller contact. Now, there's not very much load in that interface, but there is a lot of friction, or at least a lot of friction noise, a lot of ultrasonic noise will be created when you have inadequate lubrication. So I would just point out that that's a good topic for UE to pay attention to. In any case, the effects of this inadequate lubrication problem, which is so prevalent, is that you have heat, wear, and sonics, or ultrasonics, if you want to call it that. It'll have a very broad band of frequency outputs from even in the few kilohertz to hundreds of kilohertz of energy being emitted from that sliding contact. Okay, back to more interesting. Okay, we've got particles that come off of adhesion or an adhesion. There's going to be a lot of black oxides. There will be the key ones that differentiate this from corrosion, that produces black oxides and many metals, is the appearance of platelets and striated particles that have scratch marks on them, or rub marks on them. Sometimes you'll see two different metals melted onto one another. Some dissimilar metals actually in the same particle because they've dragged across one another. So these show the evidence of extreme temperature and extreme pressure and extreme force. And sometimes you'll even find sphericals because something just totally melted and the liquid metal froze in the oil to form a little droplet, a sphere. So it's pretty cool. Okay, fatigue wear is the next one we'll talk about here. Fatigue is what happens when you have rolling contact and millions of cycles. It's called high cycle fatigue. Low cycle fatigue is what happens when you have a this is high cycle fatigue, which means that it goes through millions of cycles of the roller rolling over the race, or the gear at the pitch line transferring load to the next tooth at the pitch line of that next tooth. Those kind of long-term loads cycling, they're cycling over and over again. That's a cumulative effect, and depending on how high the loads are, if you double the load, then the fatigue life will be diminished by 90%. If you double it again, it will be so 4 times increase in load will take it down 99%. So the fatigue life of a good bearing or gear or industrial component might be 40,000 hours of continuous service. Well, if you double the G forces, and that's what we use to measure load in a vibration world, the dynamic loading is measured in G's or meters per second squared. Take your choice, but whatever. That if you're running with 1 unit and you double that to 2, your fatigue life goes down by a factor of 90%. And if you double it again, it goes down by 99%. And what you see happening is stress fractures are happening underneath the rollers, underneath the surface, subsurface cracking due to Hertzian strain, which I won't try to explain in this presentation. But you'll end up in what looks like somebody has scooped out pieces of metal from the race or the roller or the cure tooth. And that's not anybody scooping anything out. All it is cracked subsurface that got interconnected until a piece of metal fell out into the oil. Okay, that is over. Next section is all about oil analysis. So now that we understand why machines fail and how they tear each other up with the most common problems, we're going to use oil analysis to try and see those and their root causes. And by the way, if you do an oil analysis program and you don't use it to impact the maintenance practices, then you better just stop because somebody thinks you're doing a good job. Oil analysis really has to change maintenance practices or you're just spending money you have to use the information. I can't tell you how many people do oil analysis like they're taking vitamin pills, and they don't really have any benefit from it. So don't do that. It's good information. Use it and change your maintenance practices based on what you hear. You get excellent return on investment, and I'll talk about that at the end of this presentation. Okay, repeating oil analysis has 3 dimensions. Normally, the wear component looks for both metals that are ferrous and metals that are non-ferrous, like copper or antimony, lead, tin. You know, contaminants are dust, water. Now, water covers 3/5 of the surface, dirt covers 2/5, and those are our 2 main enemies. Those are actually the biggest things going on here, is dust and water. And then there's process contamination too, like a lot of acids can come from some processes. And the chemistry of the oil is has got to be healthy. If you put a good lubricant in there and have the right lubricant at the right level and it maintains its healthy condition, that's a nice thing to do, and there's really no excuse for not keeping the lubricant in good healthy condition. Okay, looking at the wear thing again, how do we do this with oil analysis? Well, first of all, we need a ferrous density measurement, which means we're looking for total ferrous, something, particles larger than 5 microns. That's really important because I don't really want to know about the oxide metal, and that's going to be submicron size. What I care about is the real metal. The oxides are not metal, by the way. The truly metal, iron or copper, whatever particles you see in there, when they're metal, that means that you tore them out of the surface and there's something abnormal happening. The oxides, 98% of them are perfectly normal, so you don't want to get lost trying to chase normal. Ferrous counts, a new instrument that we'll talk about here is actually doing a total ferrous and counting all the ferrous particles larger than 25 microns, as well as counting and sizing all of the particles, ferrous or not. So that's a pretty important thing to help to use to look at wear. The next thing is a subject called shape classification. Until this year, I've always preached the idea of wear debris analysis, because you really want to know what these shapes are, and until recently, you just had to use a human being and a microscope to see them. Now, the 2-dimensional imaging camera in a particle counter can see not only the size and count the particles, but it can actually shape classify the particles and give you a complete report and analyze those shapes, tell you how much is cutting, sliding, fatigue, and non-metallic or fibers. Okay, particle imaging is really important to finding out the root cause so you can do the right corrective actions. In addition, it's very important to use, particularly for engines, but also for other machines, an elemental analysis technique looking at the very small particles in addition to the very large ones. So the small ones are best seen with a spectrometer, and you can see all the elements, 20 or 25 elements even, iron, copper, lead, tin, and we'll talk more about that. Contamination of oils, in order to see those contaminants, you care about water and you care about solid particles. So we want to count the particles, size the particles, and measure the water in the oil. For chemistry, you need to know the viscosity, because that's a basic fundamental property the oil needs to have in order to perform. But then you also need to know that the oil's healthy, and you fingerprint to make sure it's the right lubricant. And you look at the level to make sure it's the right lubricant in the right place. So in this chart, I've highlighted with a yellow star the viscosity, but then there's three different ways to see there are many different ways to see the chemistry, but typically somebody uses total acid number for industrial machines, total base number for engines, or a dielectric is something that was used until just recently. Everybody switched pretty much over to total acid and total base. A lot of other chemistry tests can be done, but we really need you to pay attention to keeping healthy oil in the machine. When you look at any kind of a mechanical system, or electrical system for that matter, things are going to fail, and you should be able to see it if they're lubricated or contain lubricants in them. So even transformers, for instance, transformers are going to wear because arcing takes place, and that arcing causes a process of wear. You know, so engines, hydraulics, transformers, gears, roller bearings, and journal bearings each have certain mechanisms of wear. They have contamination that's commonly introduced into the system, and they have chemistry problems that occur due to aging of the lubricant or other damaging effects on lubricant. So this chart's just a summary of the kind of things that you would set up an oil analysis program to look for, and I'll go into a couple of them in more detail here. Engine oils versus industrial oils. For engine oils, you need to look for the parts per million or the elemental analysis: copper, lead, tin, iron, contaminants such as silicon, sodium, potassium, boron, water, glycol, total base number, viscosity, soot, oxidation, and there's some additives, additive elements such as calcium, magnesium, phosphorus, potassium. In the industrial oils, you really need the shape classification, total ferrous particle counting, the water measurement again, particle counting, total acid, viscosity, and oxidation. So that's giving you an idea of what kind of things we need to have. Where do you get these numbers from? This is a elemental analyzer. It's a rotating disc electrode type analyzer. The way it works is an arc takes place between a rotating rotor, a little disc, and the disc picks up oil from a cup, carries it up to a spark or an arc, and vaporizes the oil. And you know, when you throw copper into a flame, it burns blue. It turns out all the elements have some kind of a color to them. And so we use that information from the colors that come off, put them through a spectrometer, split them down into their basic colors, and we can tell the amount of what elements are in that oil. This is just a chart that I would briefly mention. I'm not going to go into the details of it, but the elements that you find in a spectrometer are really useful because as you get the proportions of them, you can tell what components, particularly in engine oil analysis, what components are giving you a problem and which ones are not, because the different elements come from different parts of the machine. Or in some cases, they're contaminants like boron and sodium and potassium, or coolant additives maybe, and you find them in the oil. That means the coolant has gotten into the oil. Coolant boiled off and left behind these additives. Silicon is often an indicator of sand or dust, but it could be an indication of a sealing compound or an antifoam additive. The chemistry, as I mentioned earlier, is you're looking for the additives that somebody puts into the oil, and you don't really care what they are as long as they're the right ones in approximately the right proportions to tell you that nobody has mixed up your lubricants. Okay, Spectro has been a supplier to the worldwide joint analysis program, which is basically the Army, Navy, and Air Force for all their elemental spectrometers for 25 years now. So ever since I've been associated with them, they've done a great job, and they've achieved quite a name globally with this, and they've carried that out now. You know, the new smaller packages are being used even by this Formula One racing team. This chart shows the same information redundantly. I'm repeating myself here, where you can see the elements laid up against the wear, contamination, and chemistry vectors of the Trivector. Next technology we'll mention is the portable infrared analysis. In this case, you've got a little slide that comes out, opens up two windows. You put a drop of oil on one window, flip it closed, stuff it in. The instrument is a handheld, battery-operated instrument. It automatically analyzes the oil by passing a broadband infrared light through the oil, and looking what gets absorbed by the oil. And what's absorbed in the absorption spectra is like a vibration spectra would tell you what's vibrating. In this case, they tell you what's vibrating is the molecules. The molecules that vibrate take energy out of the beam, and from that we can tell what the chemistry of the oil is and what contaminants are in the oil, like soot, glycol, what kind of damage has been done to the oil by nitration or sulfation, what kind of acid buildup is taking place, what kind of base has been removed. So it's a pretty cool chemistry set, and it does water as well. The viscosity is being measured now with another similar flip-top machine device. It's very simple. Both of these are very simple to clean. There are no solvents. You just wipe them clean with a blue towel, and you put a few drops of oil on it, and it measures the viscosity as the oil goes down a capillary tube. And this is being incredibly successful. Everybody loves it. Okay, so you get a couple choices. You can do an oil analysis by a laboratory or a mini laboratory. The mini lab on the left is this is a combination of a viscometer, the infrared, and the elemental analyzer. And it's really good because it allows you to test incoming oils. There's about no other way to know that the supplier is delivering you clean oil, free of water, in the right additive package and the right viscosity range. Those things can cause you a lot of heartache if you don't know they're coming in. Another thing you can do with this is obviously resample. The most common oil analysis program you get is a resample request. Well, you don't need to wait to send it off and get the results back. You get it immediately. And the ownership of the program is incredibly powerful because with this device, you take the people who know the most about the machinery and hand them a very simple package to test the oil. The off-site lab has more expertise than the on-site blue-collar workers, maybe, but and there's no capital investment. If you use a lab, you're just paying by the sample. You get more extensive instrumentation, maybe, and it's actually less expensive if you're just running like 10 samples a month. So you got to trade off between these two options available to you in the plants or in the fleets. Here's a case history before I get to questions. This case history I've chosen is just one. I could do dozens of case histories. This is just one I chose for this presentation. It's actually a plant down in near Beaumont, Texas. It's a Valero Premcor. Premcor is what it was called when this was done, but everybody has bought each other, and now Valero owns it. They reduced what they call recorded failures. Now, failures in their definition were a work order had to be written and had to be worked off, and the average cost of a work order was $6,500 per repair. So they had 960 work orders that were reduced in an annual basis to 650, and I'll show you how that went. And that's a pretty significant savings of a couple $1 million, not just one time, but every year, that they can keep the number down to 650 instead of having it climb up to 960 again. I think they achieved that quite well. And they were awarded the Battle Award, which was a high recognition award that was granted to the Valero refinery. John Gobert and Jim Chrisman were the key people, and there were several others in the team there at the Port Arthur facility. I called it Beaumont, I'm sorry, Port Arthur. Okay, and this shows the answer at the end I'll get to, but I'll get to it piece by piece. What they did was in 2001, they had 995 reported work orders, and by 2004, that was down to 674. And I want to break it down as to which components or which types of machinery had what reduction in work, and how did they achieve that. Okay, looking at my clock here, okay. What they decided at that plant was they made a concerted effort to try to become a world-class refinery from a maintenance and reliability point of view. They wanted to really get rid of a bunch of plaguing issues. So they focused their attention on the lubrication program, and this chart lists the kind of things that they did in getting the program improved with lubrication specs, delivery requirements, storage, handling, sampling, training, and partnership with the suppliers. One of the first things they did was set target cleanliness levels, TCLs. The target cleanliness levels were quite aggressive, but they couldn't achieve those by themselves, so in order to do this, they partnered with their supplier. Another thing, not only in particle counting did they set their goals quite aggressively, they also said we're going to get the moisture content of our lubricants down as well. And they decided that in order to do these two things, they're going to have to do on-site oil analysis, plus they're going to have to do those other things like collaborate with their suppliers. They went to their supplier of lubricants, which was a company called Hurt Oil, and said, we really want you to deliver our oils, and we'll buy it from you in the future, but we want you to do something for us. They asked the supplier to use dedicated trucks with certified drivers. And if there are 2 compartments on a truck, each compartment will be separated, and never will oil be mixed in those compartments. And these are some of the other specifications you can see that they asked for. They got that. They basically got Hurt Oil to implement modifications to their delivery trucks, so that if there were 2 compartments, they had to have 2 sets of equipment on the back of the truck. They had to have final filtration, and they had to have 2 different delivery systems, not reusing one system for multiple lubricants. They used a 1-micron final filtration. They had the operators required to take a certain route and only come in on certain days of the week, and they had to be certified and trained, and everybody had to buy off on this. They didn't just use a different operator every time they wanted to do something, and everybody knew how important the Port Arthur facility was to the supplier, and they had everybody's full attention, so they always got the best product. In addition to dealing with that supplier, they worked with others to get clean oil containers, clean transfer containers, filters put on, breathers put on their compartments. They did sampling for the oil. They used on-site mini lab. They tagged all of the sample points, all of the storage points, and all of the transfer containers, so that no one ever misunderstood what lubricant goes in which containers. The outcome of that was they achieved a cutback in the centrifugal pump failure count, down 50% over 4 years. Average cost of repair was $6,500, and this is a very substantial cost savings. The centrifugal compressor blowers, the blowers were also demonstrating a 37% reduction over the time. Now, there was an increase in the second year of turbines, but the reason for that was they had a maintenance action that had to be worked off, and so many of the work orders had nothing to do with history. They were just a new activity that had to take place for that second year. The motor failure count did not change relatively year after year, and most of the motors are grease lubricated, so there was no impact on motor failure counts. So it serves as kind of a control to the rest of their program. The reciprocating compressors showed a surprising 63% reduction in failure counts, and that was very surprising. One would say, why is that? Well, it's because they had a change in the lubricant. In this case, this doesn't happen often, but occasionally you'll find that you've got a problem. You've selected the wrong lubricant for the application, and the lubricants that they were using were causing a problem. The problem was one of varnishing. The varnish was building up on the control valves, and so about once a year they had to perform a $10,000 maintenance action on most of the reciprocating compressors. And when they fixed this compatibility problem, and they greatly reduced the number of work orders that had to be done on this system. So in summary, the failure counts went down. The couple $1 million a year was saved, and the program was quite successful. Really nice because they got recognized by the industry, by their peers, and I'm very proud of them myself. Just a summary of returns on investment. I've got a lot of experience with ROIs, and there's a lot of ways that people save money, but I'll say that the key oil analysis part of this is being sure to do particle counting, particle size distribution, ferrous density measurements, and particle shape classification. The people that do that get incredible savings. What they see is they see deferred maintenance. They see less. What you just saw in the previous slides was somebody who's deferred a lot of maintenance by not doing work orders because they don't need to. That's a huge cost savings. Using less oil saves money. For every dollar you don't spend on lubricant, you save at least $2 to $10 on things associated with that lubricant, like buying it, storing it, handling it, disposing of the oil, and it's quite high. The lubricant purchase is a small fraction of the total cost of consuming oil. You get more credibility because the lubricant guy, the guy who has a vibration program, and the vibration analyst asks the lubricant guy about his data, will always have better information because he says, well, I see something going on. It should be generating wear debris, but I'm not seeing wear debris. So you hesitate. You just say there might be a problem. Whereas when you see both things telling the same story, you can be confident there is a problem. Because if you lose your credibility, you've lost a lot, more than money can even say. Next is it's less reactive. There are many case histories which are anecdotes that people give. I found a problem. I had no idea it was taking place. Well, you get a lot of those here. And finally, you get more accurate. A lot of people do oil analysis like taking vitamins, but they have no idea what it's doing for them or how to make money with it. So by doing this kind of a program, you get those improved accuracy, and you see some numbers on the right side, and there's a lot of publications I could use. These are some examples of publications that you might want to click on, and it'll take you to the article, and I'll be happy to answer your questions if you have them. My contact information is on this slide right here. I'm Ray Garvey. The email is rgarvey@spectrosci.com, and my personal phone number is +1 865-333 0664. And with that, I'll turn it back over to Adrian.
Okay, Ray. Excellent information here. I tell you, it's not something to take lightly. How we lubricate and how we oil our equipment for sure. A couple of questions here that we have time for before we wrap things up. First question was regarding filter micron rating. What should you do about your filter micron rating? Any thoughts on if the rating is too high, there won't be any particles, and if it's too low, there will be a high number of particles. So any thoughts on filter micron rating?
Okay, I've had people ask me questions, and then after we answer the question, they say, oh, well, I get it. I guess sometimes it's you think, well, I'm doing oil analysis, but why do I do oil analysis if my oil analysis is after the filter and the filter has taken out all of the interesting material? Why, should I take my sample from before the filter or maybe from the oil compartment or something like that? Well, the fact is, good filtration is good. I cannot say otherwise. It's incredibly important. Good filtration is now on all the vehicles you could possibly buy. You can't even buy a lawnmower without good filtration. 40 years ago, I couldn't buy a car or a vehicle of any kind that had a good filter because it always had a pizza pan on the top holding on to a donut that had birds and small animals on the outside of it and twigs and branches on the inside. So air filtration and filtration, oil filtration, is very important. Engines used to have to be overhauled every 65,000 miles. Now you never overhaul an engine, and the primary reason for that is good filtration. So filtration is very important. I cannot overemphasize that. Oil analysis is very important, and the best place to do it is right after the machine, especially if you have a really cool filter, a really good filter, effective filtration with a good beta rating, a good micron rating, whatever you want to call it, with high efficiency. What you're looking for is that gives you a perfectly white background against which any black speck immediately shows up. It's incredible if you can clean the oil up, pass it through the machine, take a sample of it, And now you know everything you're looking at is perfectly current. It only happened just now, and you're getting a tremendous insight onto the health of that machine. That's great. So do the oil analysis, especially if you're doing clean oil. Now, if you're not doing clean oil, still got to do the oil analysis. It's just you're looking through tons of garbage. You're looking through archaeology if you're looking at the oil compartment. But that's maybe all you can get is the oil compartment. A lot of machines are splash lubricated, ring lubricated, a lot of different ways that things happen. And you know, if you can only get your oil sample at oil change, well, get it and take it and use it. But I'll promise you that 95% more information if you can get it after the machine before it gets to the oil compartment. And the clean filtration only improves your results and improves your performance. Next question.
Yeah, good answer. You may have answered this as you were wrapping up and talking about calculating return on investment, but what is the typical approach to tracking return on investment by switching maintenance practices based off of oil analysis?
Good question. I always want to start before I make the change, okay? I want you to go out and collect. If you don't have an oil analysis program, go get some oil analysis results. Before you do anything else, go get some results, because that will serve, you can point to it and tell your management, this is where we were. I'll give you the example of Eddie Bowen and Frank DiArcio at GM Linden Truck and Bus Assembly Plant. They had a gearbox that failed, shut the plant down for 32 hours, and cost the plant a lot of money at $2,000 a minute. They saw the gearbox, they went out. Long story, I won't try to tell the whole story, but I'll just get to the bottom line. They went around and took pictures of the entire plant on the lubrication side, from a lubrication perspective. They found the wrong oils in 50% of the machines. They found the oil wasn't clean. They found it was misapplied. They found that 10% of the machines were experiencing extreme wear. They then cleaned up the program. They trained their employees. They put in a mini lab. They changed their maintenance practices, and they documented 736% return on investment with a $1.6 million savings in the first 26 months, something like that. Just really incredible numbers, and this is all published. So document where you start, document as you go through, and in that case, those guys invested $100,000 and got 1.6 or $1.8 million return in the first 20-some months. Then they even went on more beyond that. Unfortunately, to tell the rest of the story, because we live in America, GM finally closed that plant, but that wasn't our fault, okay? We did our best to close the plant, so, okay?
Okay, one more question and then we'll wrap up here. Ray will take the rest of these offline, but for an in-house analysis system, what is the calibration period? How often should the machine be calibrated? Is the equipment typically sent out for calibration, or is it done by the end user? And then are there methods to check and validate the calibration?
Yeah, I took those slides out of the presentation in consideration of time, but you calibrate most of these things right on site yourself. You'll run the fluid. We basically have control standards, calibration fluids, and you'll run those annually, or when you think something might be going awry, you recalibrate as needed. But I would recalibrate once a year, and or sooner if you have a reason to think you might have a question about a performance issue. But definitely you